All right, hello everyone. And today's lecture is going to be all about explainable AI. I'll try to give you a landscape of interpretable models, but first I'll start with a quick introduction. I am Venitra. I'm a fourth-year PhD student here at EPFL, co-advised by Tanya Kaiser in the ML for Education Lab and Martin Yagi in MLO. I spent some time in industry before coming to EPFL, and here I'm involved with a couple of different associations, including LauzHack, so super excited to be here. A quick outline for the talk. So first, I'll talk about what exactly is this idea of interpretability and explainability. What does it even mean? And then I'll go into kind of an overview of how current explainability methods work and what a taxonomy of these kind of methods could look like. And lastly, I'll give a quick overview of our recent research in interpretability to give you some ideas of what can be done in this space. So what is interpretability? There's this amazing book. If you're ever going to get started in this area, I would definitely recommend reading this book called Interpretable Machine Learning by Christoph Molnar. It's online, it's freely available, and he writes it very comfortably, like he's like talking to someone. So I would highly recommend it. But the way that he defines it, and I agree with this definition, interpretability is the degree to which a human can understand the cause of a decision. So interpretability is all about the why question. And to enable interpretability, this field of explainable AI has come about. Why is this field important? The first part is building user trust in models. So if a model, we've seen models in pretty much every aspect of life, from healthcare to education to all of these different domain applications that are really important. But if you want to actually get someone who's using one of these models to trust the output of the model, explainability is important, explaining that why decision. But the second important reason is auditing models when they make mistakes. So if you have a reason why and you disagree with the reason why, even if you agree with the prediction, you can know that a human should step in here and make this kind of decision instead, or know when to trust the model, et cetera. And then the third aspect is kind of improving models with their own reasoning. So let's say that you have certain explanations for why certain things have happened, or you have a training set with this kind of stuff. You can essentially use this a notion of strengths and weaknesses of a model to create customized training sets to really move forward models to train faster and understand themselves better. So with that said, what is an explanation? An explanation is the answer to a why question. For example, why did the treatment not work on the patient? Why was my loan rejected? Why have we not been contacted by alien life yet? Any of these are like an explanation in the social sciences sense of the word. But what is a good explanation is an interesting question that was answered by a set of social scientists in this really interesting paper from Tim Miller as well. A good explanation has a lot of traits. It's contrastive. It is why this, not this. It's selected. It's not every possible explanation, but it is a concise, clear explanation of what's going on. It's social, that it's in relation to the context of where you're explaining. It focuses on the abnormal. So it's not all the reasons that make sense, but also like what was the one thing that changed that led to this prediction. It's truthful, so it's not a lie, which is where LLMs get into problems here. It's general, so it can apply to more situations. It's not like exactly very, very, very too specific that someone cannot understand. And it's probable. Someone might believe that this is an explanation. And so a lot of the literature in explainable AI has been trying to move explanations towards this area. So interpretability can answer questions like, why did the model generate this output? Why did the model make this decision? And here's like a quick example from 2016, one of the like important papers that I will present to you a little bit from now, called Lime, where it basically shows like, given this text, how can you tell what category this article should be classified in? Which words contribute positively to the predictions? Which words contribute negatively to the predictions? And by what scores? That can be a nice example of text interpretability. Or another form of interpretability is kind of at the global scale. Like, what knowledge does this model have? And here we have a language model, let's say, and you can find a way to extract a knowledge graph and see what the strengths and weaknesses or what the model knows and what it doesn't know at this larger global level. And another aspect of interpretability is where in the model is this information stored? Is it in the relationships between certain topics? Do you know where exactly in the model the knowledge of cities and capitals are? These kind of things are quite interesting as well. So To concretize this very, very clearly, the way that I usually view interpretability is in the context of these applied fields like education and healthcare, or you can think of it as like a recommendation algorithm or something like this. So let's say you have students interacting with an online course or patients receiving some treatment in the hospital. Their interactions are somehow measured and then fed into a neural network. And in this case, with the students, you can predict early, let's say 5 weeks out of a 10-week course, whether they're going to pass or fail. And the objective is to give them some kind of personalized interventions, et cetera. But when you get this kind of prediction of a pass or fail, the why question is really, really important here, because you can't create disparate effects for different kinds of people without actually including that why, or maybe making concrete decisions or personalized interactions based on that why. So the problem here with using neural networks in applications like this is that deep learning trades transparency for accuracy, right? They're super accurate compared to traditional models like decision trees or linear regression or things like this. But the problem is that their decisions are not very concrete. They're not very interpretable. We cannot point to this is exactly the reason why. And so identifying why is really important for this effective personalized treatment across domains like education, healthcare, and the rest. And so the solution is this entire field of explainable AI. So now I'll talk a little bit about the taxonomy of interpretability. There are 3 main areas. It's debatable. Christoph Molnar says there's 2, but I think there's 3, so I'll present my way. There's intrinsic. Intrinsic models are explainable by design. So if you think about a decision tree, and if you're going to predict whether someone will die or survive and they're a patient, and you have a very clear set of decisions, you know that at the global level, because this is the decision that is being made across everybody, and it has like a very clear control flow, or for the specific person that follows this specific path, this model is explainable. Regardless of what input you have, you will have a reason for the prediction. Then there's In-Hoc methods. In-Hoc methods require neural networks, or not neural networks, it requires like the model weights essentially to be able to tell the explainability. So what I mean by that is, let's say you have a model that does computer vision, and I think we'll hear more from Federico later today about these kind of multimodal models, et cetera. But a model that does something like this, that's predicting whether this image is like a cat or a dog. If you have the weights, you can look at, for example, certain layers and their layer weights and the way pixels are attributed to identify which parts of the image are important in making the prediction. The simplest example of this is an attention layer at a global level, but other things like saliency maps, pixel attributions, things like these require model weights. Now, Post-Hoc is quite nice. Post-Hoc basically says, my neural network or my whatever model is a black box. How can we fit an explainer on top of it? So it doesn't require you to have access to the model weights. It just requires you to have access to being able to send things to the models and receive things from the model. And you have predictions that are of 2 classes. You have local predictions, which are like for the specific student, which features were important positively or which features were important negatively to making this prediction. Or at the global level, which features were important overall. And the global level, we'll see a method called PDP, and the local level, the most famous ones are LIME and SHAP. And so I will introduce some of those. Yeah.
Something in between In-Hoc and Post-Hoc.
I guess we'll see. So you're actually bringing me perfectly to the next slide, where I'm kind of, I have this one paper where we're trying to like create a framework or taxonomy of all of these explainability methods, or at least try to understand them from the human-centric perspective. And we have 2 axes. One is granularity, whether they're a local explanation, so only for one person, or a global explanation for multiple people or over the whole model. And then on this axis, it's from training to inference. So at what point in the model do you have to have the model to kind of like make these predictions? And all of the approaches that I'm going to talk about in the next few minutes, we'll try to place on this. I have preliminarily placed on this an approach, for example, decision trees. Because decision trees, you can have an explanation of a single person. You can have the entire framework of the model, essentially, like for any person that comes in, you would know where they would fall in the space because of a decision tree. And so it ranges local to global explanation, but it is an intrinsically interpretable model. Like you would need to train the decision tree for you to make the explanations. So it sits about there. This axis is not perfect, and we can definitely debate about this. I think it would be really interesting. But I think decision trees sit on kind of that vertical. And so I will present first a global explainability method called partial dependency plots. Partial dependency plots are quite interesting. Basically, what they try to do is find the relationship between a certain feature or two features at max and the prediction variable. So let's say y denotes the number of students that will walk into a class late on any given day. And for our features x, we have, let's say, what season it is, whether it's a weekday or a weekend, or what the temperature is, or class topic, or prior grades, and things like this. So, for example, in this hypothetical example, we don't actually have this data. We have temperature on this axis, and we have predicted number of students that are late. So when the temperature is hotter, more students are late, maybe because it's summer or something like this. But there are clearly other factors that are involved more than temperature. Like temperature isn't, I mean, as we know intuitively, probably causing students to be late. And that is probably the biggest disadvantage with partial dependency plots. It can only plot the relationship between one or two features in relation to the prediction at a time. When it gets to more features, it can't actually capture this relationship. But what is nice is this kind of rug thing at the bottom. It basically tells you how many instances it has for each point. Like, for example, at the temperature of 25, it has actually a lot of instances in its data set. But for example, beyond 30, it has very few instances, and so you can trust that part of the curve less. Okay, that's partial dependency plots. Feel free to interrupt me with questions at any time. Where I think partial dependency plots fits on this is over here. So it's a global explanation. It's covering the whole model. It's representing all of the students, patients, instances at once. And it requires the model to already exist. So it's kind of a post-hoc approach. Okay, this is probably the most famous explainer in current days. It was created again in 2016, so now it's almost 8-9 years old. But it has a really nice intuitive idea behind it. So let's take the example that I was mentioning before, where you have data about students and you're trying to predict whether they'll pass or fail from 5 weeks of a 10-week course. So now you want to explain for a specific student, X student, that fed into this black box model, why they're going to fail. The model said they're going to fail. You want to know why. So you selected your specific student. Then it has a really neat idea. It says to perturb the features of the student to get neighbors. So for example, we change the features of X student just a little bit in a lot of different ways, and we get this whole set of X prime students. And you feed all of those neighbors in through the black box model and get this entire landscape of essentially the passes and fails. And from there, you now have all of these X prime students and all of these Y prime responses from the model. And what you do is you want to train an interpretable model, let's say a decision tree or something like this, using a weighted sense of the X primes and Y primes. So basically, this is now your new training data. You feed it into a decision tree, but you've weighted each of the points based on how far away they are from the original student. And from there, you can get a very clear idea of why the student was predicted this way, because in changing this, you saw that the decision flipped, et cetera, and which ones are more important than others. So this is kind of an intuition behind how Lime works. SHAP is probably the second most popular and probably even more popular these days, or rising, as an explainer. What it does is it quantifies the contribution of each feature to the prediction. And so you have a black box model, you have X student and Y student. So you have a specific student, they pass through a prediction and they're going to fail, which is unfortunate. Let's say in our model, there's only 3 features. So there's number of minutes watching videos, there's number of clicks on problems this week, and there's number of sessions that they've participated on Moodle or something overall. Okay, great. The way SHAP works is that it deals with the power set of all of these features. It says that you cannot quantify the contribution of each feature alone, but you need to think about features in combination with each other. And so what it tries to do is train a model with no features at all, then train a model with only feature 1, then only feature 2, then only feature 3, and then train a model with every combination of features, and then train a model with all of the features together. So already this is 2 to the 3 models. This is 8 models. But you can quickly imagine that if you have, let's say, 45 features or 50 features or hundreds of features, this becomes super problematic. So that is kind of the disadvantage with SHAP. But essentially, you train a model on each feature coalition, and then they have a really neat idea. They're looking for the weighted sum of marginal contributions for each feature. What does that mean? Let's look very concretely. So now let's say you want to find the weighted sum of feature 3. So this model here is involving feature 1 and feature 3, and this model is only involving feature 1. The difference between their predictions for this point is the marginal contribution of feature 3. And now you do that for every combination where feature 3 is kind of added, and you weight all of those together into some kind of weighted sum. And that's kind of how SHAP works. And you have to do this again for every feature to create a score. So really computationally expensive in its original form. But there have been several optimizations with things like kernel SHAP and permutation SHAP using different kernel functions or antithetic sampling to make this a little bit faster. Any questions? Yes. So here, for example, where I was showing that we have a model with F1 and F3, and we have a model with F1. And for a specific prediction, let's say a specific point that we had, this model made a prediction, and this model made a prediction. And the difference between that prediction is you can attribute it to the addition of feature 3. And so when I say weighted sum, I think you weight the feature 3 one, like based on the order of cardinality of each of these levels, you weight those more. So the difference between feature 3 and null, which is no feature at all and just feature 3, is weighted more heavily in the sum than this difference between feature 1 and feature 3 and feature 1 and etc. And there are lots of equations in the paper. They're very cool. I would recommend reading them. So I'm just trying to build intuition here. But there are also different ways of doing the weighted sum. Okay. So where does this fit? Lime and SHAP, I kind of put here at the end, but I do agree with Peter, right? Peter's point that SHAP does require access. I mean, it doesn't require access to the original model. It's training a whole bunch of new models. So in that respect, I consider it post-hoc.
Why do you prediction of SHAP? But if you use kernel SHAP or
Fair.
SHAP or Bayesian SHAP or all this stuff, it becomes
More complicated. Yeah, sure. The variations of SHAP fall somewhere in the middle, but definitely SHAP can produce both local and slightly more global attributions because it's creating scores for features. And if you take them over a large population of people, it could be interesting. Less local, for example, because you're training larger models based on all the students. Okay. Now, counterfactuals. The CEM is a counterfactual method. It stands for contrastive explanation method. It's a little bit harder to build intuition about, but there are two aspects of it. A counterfactual, how many of you know what a counterfactual is? Nobody knows what a counterfactual is. Okay, so a counterfactual is basically like, I am a student, and let's say the model predicted that I failed. What would a neighboring student to me be like if they passed? Like, how would I change such that I could now be a passing student? And that new fake passing student is your counterfactual. So in this case, CEM is a counterfactual method. And it has two aspects, pertinent positives and pertinent negatives. So basically you have your own original student X, and you're trying to create an X prime such that these hold true. So you have pertinent positives and pertinent negatives. And let's say certain features are positive and certain features are negative. And a way that you can create a future importance score to like compare an approach like this with Lime and SHAP is to kind of find the distance between the newly created counterfactual student and the student that you actually are interested in. And then DICE is another, yes.
Explicitly putting counterfactuals and none where you're doing perturbation from
Yes.
real sample. What's the difference?
So with CEM, it creates one counterfactual. And it has certain, I guess in this case, it creates two, one with pertinent negatives and one with pertinent positives, depending on the way you call the CEM library. But with Lion, the perturbation is a lot of random noise, like Gaussian noise, to create a lot of different perturbations. So really, all it's trying to do is say that for Lion, the intuition is that you have this student, and you have perturbed the student in all of these ways surrounding the student that the student could be. And you're using that to just explain where the decision boundaries are for the student. So it's really like amplifying the local neighborhood. And there have been studies that have come out actually showing that the neighborhood selection in Lime can change a lot about what the explanation is and how do you know what is a good neighborhood to select of points around Lime. So in this case, it's basically finding the optimal counterfactual for you. And it's actually really relevant in cases like education, because like this is the student you are, and this is the student that you would be if you passed. And what is the difference between these two could directly lead to an intervention, right? Like, oh, you need to watch more videos on week 5 and maybe do that problem set. Okay, you can do that.
Maybe I'll come back to this later because I'm not sure I get it, but maybe more that you explain.
I think probably this might make it clear. Yes, I'll take the question.
In general, what I understand, like in a deep neural network, it kind of approximates the mapping from the input to the output, but it doesn't learn like in between the layers what's the mapping in between them. We don't know exactly. And in that sense, the model is interpretable, right?
Yes, but I will show you a bit in the future some of these newer interpretable by design models that actually revealed the process a bit more.
What I asked is, this field is in essence try to understand in between layers as well, like the mappings that has to be learned in between the layers. Like we don't know for now, like how does it learn in between the layers?
So there is.
We don't know. There is some weight matrix. There are some correlations between them, but we don't know what kind of correlations are there.
For sure. I guess that point that I was mentioning at the beginning, there is this field of NLP called Bertology, and now it probably has a different name, maybe mechanistic interpretability. And what they're trying to do is exactly this: find like relationships between models or deep into models where information is stored and how these layers interact together. And whether you can, like another extension of this is like, can you delete specific information from a model? And for that, you need to know where in the model that's stored and how you can remove it or how you can train a model to forget stuff. All of this does exist, but it's quite bad right now. It's not really effective. And so I'm presenting the stuff that is actually used in applications as well, in the real world. But I will show you in a little bit that these are also bad. So DICE is another counterfactual method. And this one is like the most intuitive way of counterfactuals. So you have a person, they've decided to fail, unfortunately. What is the closest person to them that will pass? And it does this by optimizing the DICE loss and the determinal point process metric. But essentially, this is like the stereotypical example of a counterfactual, where what is the next point with the smallest possible change that flips the prediction. Okay. Just a case study, because there's one important point about all of these explainers that I'm presenting. In the education space, there usually is only one of these explainability methods used across many different papers. Like people are like, okay, explainability, I'll choose one of these, I'll hit it at my neural net, and this is what the explanation is, and this is what we've understood. Cool. But what we're interested in is maybe comparing across these different explainability methods that I just presented to see which explanations are maybe more relevant in which cases. And what we did is in a model just like the one that I was saying. Let's say you have a student, you're predicting early in a course whether they're going to pass or fail and identify why. What we found is that across all of these methods, there is a lot of difference in which features they find important. You can see that Lime is super sparse, CM is quite different than the rest. And across multiple courses, we see, this is Spearman's rank order correlation. All it says is it's comparing, let's say, the top 10 features and their ordering, and it takes that into account when comparing them. And this is relevant because a teacher can only make a decision on X number of factors at a time. And really, this should have very few colors on it, but it has a lot of colors on it, which means it's quite problematic. And probably the most interesting graph from the paper called Evaluating the Explainers is that looking across these methods, for example, kernel SHAP, perm SHAP, which are two variations of SHAP, they're quite similar to each other across 5 courses, cool. But you see clear clusters by explainability method and not by course. So you would expect all of these pluses to cluster together because they're the same students from the same course, which should have the same explanations of why they pass and fail. But actually not true. When you choose an explainability method, it biases a lot what it considers important in an explanation. And these results were also confirmed by a very large study from Harvard, CMU, and a lot of others called the disagreement problem in explainers, where they identified that across a lot of different use cases, post-hoc explainers disagree with each other. And it's super problematic because I urge you, if you're going to do explainable AI, have a reason for which method you select that is relevant to your application, or use multiple maybe, and use the ensemble of them. But don't use just one. And so my intuition in my research was, okay, these methods kind of systematically disagree. How can we build trust in them? And maybe human experts have the answer. Like we can choose a task, which is easy for human experts to identify what is important. Like, for example, we can find experts of this exact like student performance problem that have been professors that have taught a long time, especially in MOOCs, and they would know what behavior is successful or unsuccessful, or at least which explanations they trust more than others. And maybe we can give a pointer to our community to say, maybe this is trusted by this many professors, and maybe you should start using this. And so we interviewed 26 STEM professors, and trust me, scheduling this was a nightmare, that were quite diverse in geographic location, all of them in like 45-minute interviews where we gave them a lot of different points and trained them on how to answer these kind of things. And all of them had taught MOOCs before. And so we also chose courses that had a clear difference in learning science behavior. Like, for example, it's the same course offered as a MOOC versus in-person or flipped classroom kind of course. Taught by the same professor. The only difference is the student populations and the modality or something like this. And we gave them Lime, SHAP, and a confounder explanation that was kind of based on counterfactuals. And what we found out was that all of these professors actually have diverse prior perceptions of what factors create student success and failures. And so the explanation they trusted aligned with their beliefs almost 50% of the time. And this therefore led to significant disagreement across experts because they believe in different things. But what was most interesting was that actually we presented multiple of these different explanations and tries for them to look across different courses. And only 3 of the 26 professors chose the same method twice. So explainability methods systematically do not agree, and neither do human experts. So my research has mostly moved into this intrinsic area, the intrinsic and in-hoc. How can we build neural networks that tell us immediately like what the explanation is, and it is what the explanation is? Yes.
We use some metrics to identify which explanation is more trustworthy in a given task.
So if you read the Evaluating the Explainers paper, we actually have this very cool validation where we have the like course map of skills in a course. And so you know that let's say the skill that you learn in week 4 of the digital signal processing class here at EPFL, taught by Paolo Perdoni, is like related to the material that you learn in week 3. It's like a direct prerequisite. So ideally, the information that you learn in week 3 should be important for week 4. And we did this for like 3 other pairs of weeks in the course. And what we found was that, yes, all the explainers did find the week that was the prerequisite week quite important, but they all found different features in those weeks important. So they're not all wrong, but they can't all be right either. I would encourage you to read the paper maybe. And if you have better ideas for trustworthy metrics, I think there are a lot of people working on this space. There's stuff to be done, but I think the community has finally agreed that these post-hoc explainers don't really agree with each other and can't be fully trusted. However, there are still tons of people who use them. So if you use them, try to use more than one. That's all I'm saying.
How to combine different methods together.
No, because well, I think it's really important and relevant. And in the second paper, the one where we interviewed teachers or professors, we do have a long quantitative section where we do use multiple methods together, like the ensemble of methods. But in the first paper, it was mostly like, this is a problem that we didn't know exists in this community. And we need to stop doing it. Sure, but I wouldn't say that I'm the expert on combining it. There's probably a lot of other literature. I would look at Hima Lakaraju's lab. She's always doing cool stuff. Lakaraju, it's the XAI for Life lab or AI for Life lab at Harvard. Yeah, no worries. So where do we go from here? Intrinsic methods, explainable by design methods, or in-hoc interpretable neural nets. So I'm going to rapid fire present a few ideas that we've worked on in the ML for Ed and MLO labs, and I'll leave it up to your perusal of where it can fit on the axis. And then after that, I do have some code that I can show you, but let's see if we have time. So the first is kind of to frame the rest of it. I think it's important to know about what human-centric AI needs are for explainability. And so we present these 5 needs across a lot of different applications of legal stuff, education, healthcare, et cetera, where people request these kind of things and explanations. And we have a user study also on this that hasn't come out yet, but I will keep you guys updated. So people care about consistency, that multiple generated explanations for the same point are the same. Not across different methods, but across different methods, but even across the same method, when you initialize it, for example, with Lime, there's random noise that are creating the random X primes, and that could lead to a very different explanation across multiple times of running the same Lime. So that's concerning. Explanations need to be real time, but what real time means differs across different applications. Can it be within the next minute, the next lesson, 1 week after the course? How important is real time to explanations? Accuracy, which means that can the model display a level of confidence in the explanation? Is this explanation guaranteed to be true? Or is it like Lime, SHAP, and the rest, like an approximation of what the neural network is doing, and there's no confidence score attributed with these kind of approaches? Is it actionable? And this one's actually my favorite, because I think it's actually the most useful. Are people able to take a next step based on the insight? Is it actually useful to a human to have the explanation beyond just, okay, good, I have an explanation? And the last part is human interpretable. Is it easy for a non-data scientist to understand this explanation? Yes.
What does it mean for the explanation to be correct? What does accuracy mean? Other than the model says, I think it's correct, and I'm very confident that it's correct.
Well, so the approaches that I'm going to show you, hopefully, are like guaranteed to be correct because that is what the model is doing. And the explanation is what the model is doing because, like, for example, a decision tree, guaranteed to be a correct explanation because it is what the model is doing. With Lime and SHAP, and everything else, there are lots of degrees of randomness across all of these approaches or random seeds and stuff like this that can cause quite a lot of variety in explanations. And so is there a good way to measure that? And right now, no one has created a way to measure that. So if you guys are interested in research, I think you should work on that. Okay. So one paper that is quite recent from our lab is called MultiModal. It's all about multimodality and interpretability together. And we'll hear more about multimodality later today, which is why I wanted to mention this quickly. But multimodality is super cool. It has like a lot of synergistic, yeah? Yeah. I wonder, can Bayesian probabilistic models be used in XAI? Great question. Totally. There is, I guess you're talking about like Markov models and the rest. There is a lot of work on this thing called like interpretable deep knowledge tracing. I mean, there are different Markov models used in various different aspects. It's just that our world has kind of moved towards neural networks. So that's why this is kind of the most pressing XAI problem. Because Bayesian processes are interpretable by design, but they do not perform at the same level as neural networks for a lot of applications. So that's the difference. So with multimodality, you have inputs with drastically varying sizes. Let's say images, text, sound, video, different modalities. And current approaches take all of those different modalities and fuse them to the same representation space. So you take these different inputs and you map them to the same kind of embedding space to leverage their shared predictive potential. But this approach kind of limits interpretability. How do you know which part of the input actually made a big difference in the prediction? And then the second part is that it creates a dependency on modality availability. So let's say you train your model with videos, audios, and text, but then you go to an environment, let's say a low resource environment like Africa or India or something like this for your medical model, and you no longer have access to videos of chest x-rays or something like this. Then the model has already learned patterns that don't exist in your current input data and therefore will bias the response. And so to address these concerns, but also to kind of enable interpretability by design, we present this architecture called MultiModal. And P-fusion is kind of what current multimodal architectures are a bit like. And I think Federico will speak more to the latest advances in these. So they might be a bit different. But there are images, for example, there's text. Let's say there's time series, but maybe it doesn't exist now. This missing input would be padded or encoded in some way, and then maybe masked or not masked. But anyway, when training in the same shared embedding space, all the embeddings are like concatenated together and then trained on like fused representations. And then you'll usually have, let's say, a single task decoder, like a decoder for each task that the model was trained on for some specific task. And then you can use that general representation maybe for other tasks, but it was only trained to perform this specific task. On this side with MultiModN, what you have is, for example, these images are passed to its own separate encoder. And inspired by RNN architectures, kind of where state moves over time, you have a notion of a state of an average patient or an average student or an average input for any of your networks. And a number of decoder tasks. Let's say these can range from regression to classification or whatever tasks that you want to include. And you have this notion of an average vector or a learned vector representing your average student or average patient. That vector gets passed into an encoder that is optimized only for the specific modality that it has. So let's say this encoder only takes in images. And those images and the previous state output a next state. And from this state, it's decoded on any number of tasks. And then this state is fed into the next encoder that takes only text and the previous state and outputs the next state, and then that's decoded on any number of tasks. And the advantages to this kind of architecture, one, we proved that this kind of architecture is at least comparably performant across like 10 real-world tasks to the other kind of architecture. But the advantages are more interesting. In terms of interpretability, it can do both global, which is over the whole model, and local interpretability. So you can identify which modality is the most important for this task. which you can't really find in P-Fusion. Or you can identify which modality caused the decision to flip for any specific person for a diagnosis or something like this. And of course, in each of these encoders, you can employ more traditional interpretability techniques like attention or anything else to be able to describe in more detail what part of each modality exists. But the fact that this is already interpretable by design, you can extend it instead of each modality to be each feature if you really have few features and you want to use this kind of architecture for that. And then the other cool advantage of MultiModN is that it's robust to bias from missing input. So when there is some data missing in the train set and a different kind of data missing in the test set, traditional architectures do quite terrible. They exhibit this like catastrophic forgetting. But MultiModN is quite resistant because the missing data is never encoded in this architecture at all. Like data that doesn't exist in the test stream just simply is never encoded. That encoder is just never called. And because this doesn't feed into the state, it doesn't have this catastrophic forgetting. And this is super relevant in low resource settings. And actually, this architecture is now being used in some clinical trials in South Africa for tuberculosis detection. So we're really excited. We believe it works, but let's see. And so this architecture matches parallel fusion, P-Fusion, on a variety of real-world tasks. It's composable at inference, which is super nice because you can always add more encoders or add more decoders very composably. It's robust to missingness. It's inherently interpretable for a definition of interpretability, and it's easily extended to any number or combination of new tasks. So where it sits in this, I think, is here, because it has both local and global interpretability, so maybe it actually should have been in line. And the model is intrinsically interpretable. Yes.
Can you speak a bit more about what you mean by catastrophic forgetting?
Yes.
And specifically, so the thing that confuses me is, how can you forget something if you were never shown?
So
So maybe it's just the term, and the term has a little bit embedded into what the term means.
it's possible. I'm not so familiar with the terminology. I know this terminology is really relevant in medical AI. So Mhm.
Like if you saw the previous Gaussian, for example, then if you saw the next Gaussian, it just remember the next Gaussian, not the previous.
exactly.
That's the MLP, I don't know about it.
So what you have on the x-axis here is the percentage of missingness not at random. So specific missingness in the train set. So here, when 10% of the data is missing, it's not so bad. But when you get to like, let's say 50% missing, it's quite bad. And 80% missing, it's really bad. And MultiModN is also bad because it has less data. But it is not that bad.
Okay, I just don't, the query I have is just, I don't really understand what it means to.
Catastrophically forget something.
Catastrophically forget what you never saw. That's the only thing I don't get, because you can call it, I'm just less performant when I don't get to see data.
But it's not exactly this, because you have a different set of missingness in the train set than in the test set. Okay, I guess it's
Just to do with which things.
yes, but in both of those cases, not everything is missing.
Yeah.
Like at max, it's 80% missing. So it's not 100, like they're never, we're not giving them a new modality they've never seen. We're giving them a modality they've seen 20% of or 50% of or something like this compared to the entire data population. Does that make sense? Yeah. But it's a good question. Hey, I've never thought really about what catastrophic forgetting really means.
This slide?
This slide?
Yes, this one.
Oh no. Okay. I cannot defend this very well, so I accept all opinions.
Why put it like close to decision tree? Because like when one modality is missing, we can understand like how important it works. But inside the modality, like given an image, we still need to identify what is important inside in the image itself. So it will be more post-hoc, we still need to use line or SHAP, I guess, to use.
You could use attention, right?
Attention,
Or pixel attribution or any in-hoc method as well.
but it will be post-hoc methods then.
No, those are still in-hoc methods. Like for example, in most of the image stuff, if you're not thinking about like Lime or SHAP, but you're thinking about pixel attribution or even just attention over an image, it is in-hoc method because you need to know it's just like a weight layer in the model. So you do need to know the model weights.
Post-hoc, we don't.
You don't need to know the model weights. But good. Okay, Riffle is an in-hoc method. So can we obtain interpretability on raw multivariate time series? So time series is kind of an interesting problem because no one can, like, a human just looking at time series is overwhelmed. And a lot of like the data in education is actually time series, people's click streams that are associated with their interactions with like a learning platform, or if you think about a hospital, like the test measurements and stuff like this. And usually, even in the previous papers, we extract features from the time series through frameworks. But a normal educator in, let's say, an English classroom or something like this isn't going to do that. They want to just press a button and get kind of the raw click streams from Coursera or edX or whatever their data dump and put it in something and have some insights. And so concept activation vectors is a really neat idea from Bean Kim over at Google. And you can create concepts based on examples. So you can create a concept of high effort students based on like students that you know to have high effort. Let's say you have like 30 examples of high effort students, and you have random students, just like a randomly selected sample of students. And you see how much for a specific concept it is used in the prediction, whether the weights are kind of towards the directional derivative of some of the weights are towards the direction of the high effort vector or towards the direction of the random student vector, to see whether, for example, the example that they use in the paper is quite nice. It's like you have a zebra and you define the concept of stripes because you have a lot of images of stripes. And you're trying to see whether the concept of stripes was used towards the prediction of zebra or not. And that can also help you audit the model, right? Like if not, what's separating a zebra from a horse? Probably that's where your model is going to make a mistake. So there is some cool stuff about this. It's both global and local scale. You can see this over the whole model or over specific students. And you can also do user-specified example-based concepts, which are kind of easier for humans to specify because they're like, oh, is their relationship to these students or this factor, like the people doing no work on assignments, was that used for classifying this student as pass or fail? And it directly uses model activations. So it is accurate to what the model is doing. So yes.
That's correct. That the idea is that the human tries to understand how the model works and then uses this method to see whether it indeed uses this thing in the input or not.
I think the first part of your statement is the only part that I think would be shifted, which is that it can be even at the beginning. The human specifies, let's say, 6 or 7 concepts by examples that they think would be important to the model, or that they believe, like, for example, if you're deciding whether to give someone a loan or not, you believe that people with high income or low income, like the difference between like a high income feature and a low income feature should be used somewhere in the prediction. And you have race as a variable, but you're like very concerned about it. And you define a concept of like people from this specific race, and you want to see whether it's used in the prediction. Yeah, I mean, the concepts have to be defined before the interpretation, but you don't have to have the model first. You could define the concepts first as part of the data preprocessing. And that's why it's kind of in the in-hoc explanation area and mostly local, but you could do global also. Okay. Last few ideas. Interpret CC. This is our recent preprint. It's about intrinsic, so it's an explainable by design approach using global mixture of experts. And how it works is this. We have a bunch of features, let's say, and a human or a language model or something like this classifies them into some groups. And we have a discriminator layer. This discriminator layer decides whether to activate certain groups or not, and which groups is it more important to activate than others. Essentially, with the sparsity filter, trying to select the least number of groups that you could use to make a prediction. And then there are a whole bunch of these different experts that have been trained only with a group of features that someone has defined as relatable to each other. And you can create kind of like a weighted prediction from these. You can see which feature groups, let's say the feature group of watching videos and all of your features relating to videos is, I think, 70% important from the discriminator layer, and then 30% important is quiz scores. You know that this prediction was only made using those two things and not any of the other features that are available in the model. And there are a lot of variations of this in the paper, but it's kind of a nice idea of routing for concrete interpretability. And if the human specifies the feature groups, it is interpretability that is actionable, right? Like they're defining what is important to them that they can make a decision on. So there's this, which I think sits here, debatably. And then some of the last work that we're working on is about like AI writing support will bias from model suggestions transfer to students with Parsa as well. And then we have some papers on using GPT-4 as written feedback on student assignments. Not really explainability stuff, but tracking this bias along the pipeline is kind of a global interpretability problem. So explainability and bias are intrinsically linked, or fairness. I think fairness is enabled by explainability or interpretability. So we have to be able to explain models' decisions to know where it's going wrong. And then the last part that I wanted to explain is kind of a work that I'm working on right now. So if you look at what explainer output actually looks like, it's terrible. Like for each feature, for each student, there are certain importance scores. And these are what, 4 columns? There's 450 of these columns for each student. No teacher can possibly comprehend this, even if you select the top 10. Because like if you look at the features, it's like total clicks in week 1. Okay, like tell them to click more. Like it's quite difficult. And if you create heavily processed visuals, which are like the ones in my papers and other people's papers, you get visuals that look like this, kind of like these heat maps that you were seeing earlier of which areas are more important than others. Or this is the validation study that I was talking about. You can see like, for example, student speed in weeks 4 or 5, which is how fast they are at answering quiz problems, is important, and that can indicate something. But this requires really a lot of human effort, both to create the visualizations and to actually like understand them. So maybe we can use LLMs for this. I don't think LLMs should create explanations, by the way. They're just going to tell you what you want to hear. They're not going to be accurate explanations, at least at this level. Maybe with RAG and stuff, it could be better, but I don't know. But you could take all of these terrible to understand explanations, select what's important in those, and package it up nicely into like some kind of actionable insight. And then eventually have happy students and teachers because they have improved learning outcomes. That's the goal. But doing these 2 steps is actually really hard. We're turning to actually a lot of different social science theories of explanation, because they've actually figured out how to present explanations to people and how to extract what's important already out of an explanation. And so we're using kind of LLMs to use those social science theories on the outputs of explainers. So hopefully people will find certain ones of them actually useful. And maybe this is a nice way to bring LLMs into the explainer loop. And that probably sits here because this is on an individual basis. It's not creating global explanations. But it could. Anyway, that's a point for another time. Anyway, thank you so much.